This is lecture number 15. Let's begin with the review of what we have been doing so far for the last two lectures. Yeah, we have been still spending time on explaining the Shor's algorithm or factoring algorithm, and then the essence or the outline of the Shor's algorithm generally starts with some random number which has nothing to do with the number we want to factorize, and then we create a superposition of all 0, 1, 2, 3, and so forth up to 255, and then using that value as an A. So, and then we calculate the power of 7 when it is within the frame of the mode 15. So what we are left is eventually is this remainder after we calculated the division with the integer division divide by 15, and then these are the remainder. And then if we just summarize this remainder, then this value has some kind of period. And then typically we generally store these values in the additional register. And then if we collect all the terms which has the same remainder value, then the initial index representing 0, 1, 2, 3, so forth will be grouped with some kind of period. And then yeah, that's so finally to find out that embedded period, what we need to do is applying the quantum Fourier transform. So yeah, if I rewrite that situation, if I give you more detail about what happens, and then initially what we do is we create the superposition of all these indexes, and while for the encoded register, we just start with the definite value of 1. And then after we calculate all these power of that R value, some random value, then yeah, we will have this kind of pair like index and the remainder index and the remainder after calculating the power of that random number using this value as the exponent and so forth. So after we obtain these, we note that all of these term has the same factor like 1. So we extract we just collected all the terms while factoring out the one part. Then we will be left with this kind of superposition of 0, 4, 8, and so forth. And then for even for the other cases, they still have the same pattern. Yeah, so meaning that the basis vector will be different by number 4, and then they will keep repeating like this one. So the question is, when you are given one of these vector, yeah, you might assume that you simply just measure the this encoded register, which is stored here. So if you got any value like 1 or 4 or 7, then you will collapse this proportion into one set, and then you will be left with one of these a vector, whether you might have this this vector or this vector, we don't know. But the point is, yeah, whichever you have, they are all separated by 4. Yeah, so yeah, and then the result of Fourier transform actually, the details of the Fourier result of the Fourier transform is a little bit different, but overall, what we care about is basically identical. So yeah, whichever was obtained, it doesn't matter. So we should somehow understand the process of the quantum Fourier transform. So I started by explaining about the discrete Fourier transform, and then I turned that one into a quantum Fourier transform. And then eventually the function of the quantum Fourier transform corresponds to, it is similar to basis transform from this computational basis to this superposition of many computational bases. So yeah, let me give a little bit more detailed review. So the purpose of the discrete Fourier transform is the following. So you are given this kind of sequence of the numbers, and then we are wondering what kind of sinusoidal or periodic sequence is embedded inside this sequence. So the way we do is, for example, we might have some kind of periodic sequence component inside this one, something like this one, changing like this this kind of sequence with this period. But there might be also other components like which is changing faster, and then if you have some kind of much or where maybe it is easier to draw some slower sequence. So in that case, we might have very slowly varying sequence and then this total sequence might have some component which is changing faster like this one, or much slower like this one. And then the amount of component embedded in the entire sequence can be obtained by discrete Fourier transform, and then eventually you will be left with something like y0, y1, and so forth with the y sub k, and continue until you will obtain n-1. And then the question is how we can obtain those, and then if you remember that this y sub k can be expressed as square root 1 over square root of n, and then summation over from 0 to n-1, and then the value for this one was obtained by multiplying each of these components with the typical this kind of shape. Yeah, so 2 pi I, and this subscript k appears here over n, and finally this j is multiplied here. However, if you look at this problem carefully, this one is kind of sampled value of this kind of continuous function, like like this one. And then for this sinusoidal curve, typically this might be something like 2 pi I omega t. And then here, what happens is we replace this t with index j, and then instead of having this continuous version, we might just sample some of these value. So that was the meaning of this one. And then which part corresponds to frequency? And that part is actually this part. So these are the frequency of this one. And then as we increase this k value down to here, then what we are doing is we are collecting the coefficient as we increase the frequency value. So each of these y value corresponds to the component of higher frequency component. And then this is the classical discrete Fourier transform. Then what is the quantum version of quantum QFT? So what we in the quantum version, what we want to do is process some input vector, and then based on the vector information stored in the vector, we want to calculate some corresponding discrete Fourier transform. And then in that case, we should first construct the vector corresponding to this given sequence. And then the way we do is we create a vector in superposition of 0 and 1 and 2 and so forth. And then for this case, we use the given value like a x0, x1, and x2 as a coefficient. And then what we hope is that after the processing, the output state will still have the each of these result as a coefficient again. Yeah, so something like this one. So that's the ideal goal. And then we want to figure out what kind of thing this linear operation does, or the unitary operation does. And then because this is linear, yeah, to figure out what this is doing, we don't need to provide all types of combination. And then in linear algebra, yeah, for the linear operator, if you want to figure out the function of that linear operator, all we have to do is just to provide some elementary vectors. And then in this case, elementary vector is one of these all of these computational bases. So instead of providing any arbitrary linear combination of any vector, we will just select one of the basis vector like a j, and then we feed this vector into the QFT circuit, or QFT unitary operation, and then we will still be left with this kind of 0 and 1 and 2 and so forth. But we can immediately find out what this value should be, because in this case, we are not considering the superposition, but we are considering the vector which has only j sub x sub j is 1 and all others are 0. So that corresponds to so if I and then all the others which is not j are 0. So if I plug in this kind of sequence to this one, then all the other terms will be 0, and then only one term, which has the index j, will survive. So yeah, and then in that case, this value is also 1, so we can ignore this part, and then we can only keep write down this one. And then in this case, I is the index. So yeah, for the first term, what we need is 2 pi. Sorry, this I is not that value. Sorry. So this value corresponds to this index, and then that is here, and then this I is the imaginary, implying the imaginary. So k is 0 over n, and here I should have a j, and then the second term will also have a similar form, but here instead of 0, I will have 1, because here is a k, and then here is a j, and the next term will be also 2 pi. Oops, this was not j, this was I, and this is 2 pi I, and now k is 2, so 2 over n, and then multiply by this one. So overall, what I can see is that if I start with the j, then the QFT transform, then the QFT unitary transform actually turns this basis vector, or the computational basis, into a summation of all these components from k equals 0 to n minus 1. And then I also forgot to mention that each of these one will have 1 over n, 1 over square root of n, and then each of the vector, k from 0 to n minus 1, and then the coefficient of this one is 2 pi I, and this is k over n, and then this j appears here. So that is the relation we need to figure out. So what does that QFT circuit does is when this J vector is given, this this computational basis is given, then it will produce some new vector, yeah, looking like this one. So yeah, let's see how we can create this kind of circuit. If you read section 5.1 in the textbook, then it generally describes the QFT circuit by showing the result that the previous the relation for the transform of QFT corresponds to this J basis being mapped to a new basis composed of this shape, and then eventually, if you just work out the math, then you can rewrite this state in terms of this form, and then it explains how we can implement this kind of result using the circuit. But I assume that many of you are not familiar with this type of derivation. So let me work out some details. So the question is whether we can work out or re-express the given expression here in a little bit different representation. So before we continue our discussion, let me simplify some of the situation. So for the capital N, which is the number of the length of the sequence, arbitrary sequence, we will only consider the power of the two. And yeah, for further example, yeah, I will narrow down even further. But before I continue, let me also define some of the notation. So typically when we write down just the J, this we are just assuming that this is expression in the decimal number. But we know that if we have decimal number of 5, then if we want to express this one in terms of the binary number, and then if we want to express it using three binary digit or 3 bits, then it will be expressed as 1, 0, 1, 2, meaning the binary number. And then yeah, we will also use the notation that we will refer the first digit as J sub 1, and then second digit as a J sub 2, and then third digit as a J sub 3, and so forth. And then yeah, this can be also considered as yeah, there will be some kind of expression like this one, and then the yeah, and the meaning of this binary digit expression is that J1 is actually multiplied by 2 to the 2 to the second, and then the J2 is multiplied by 2 to the first, and then J3 is multiplied by 2 to the 0th. And yeah, so this, and if we had even further, and then if we generalize even further, if we had n bit number, then it will be something like 2 to the n plus it is 2 to the, sorry. It will be 2 to the n minus 1, and until we will have j sub n times 2 to the 0th, something like this one. So this is the typical meaning of the binary digit, binary number. Then what happens if we have not only just the typical binary number, but with some decimal point, or I should call this one as a binary point. And then yeah, we have some binary fraction like this one. Then yeah, still the meaning of the first one is, or the first digit means it is 2 to the first, and then the second term, second digit means 2 to the 0th. Then what about the first digit after the binary point. This the meaning of this one is 2 to the minus 1, and then the second the 0 here is 2 to the second 2 to the minus second, and then the third digit is 2 to the minus third, and so forth. So more generally, if I have only the 0 point here, and then the meaning of this one is actually more generally, if I have some number like j sub 1, j sub 2, j sub 3 in the binary digit format, then the meaning of the value of this expression in terms of the decimal point is that not decimal point um, in the expression of a decimal digit or a decimal number, then it is j1 times 2 to the minus 1 plus j2 times 2 to the minus second, and then j3 times 2 to the minus third, and so forth, if we had more digit in the following. So yeah, this is just a format of the this is just the format in a binary number. But let's also and then the one of the claim in which I just showed you in the previous page is it is asking whether I can express this one in terms of J1, J2, J3, and up to J sub n. Then whether that QFT can be expressed in this way, e to the 2 pi I times 0 point j sub 1 and 1, and the second term will have e to the 2 pi I times j 0 point j sub 1, j sub 2, 1. And if it will continue, and then the final term will be expressed as e plus 0 plus e to the 2 pi I times 0 point j1, j2, and up to jn, j sub n, and multiply by this one vector. So how can we express this one in terms of this one? So in this case, we have to consider some more concrete example. So let's consider about the case when we have capital N equals just 4. And then, let me just copy this expression one more time because I need to keep using it. Yeah, so I'm going to use this expression over and over. So let me just start with a simplest case when the j equals 0, and then what this expression says is that let me save some more space because I know I will need a lot of space. So this one is expressed as because it is 1 over square root of capital N, and in this case, I'm assuming that capital N is 4, so it is 1 over square root of 4. And then when we have j equals 0, and then the summation goes from 0 to 3, and in this case, if j equals 0, then the exponent part will be always 0 because j is 0. So we don't need to consider about any of the exponential value. So all we have to do is just add from 0 to 3. So I will just write down 0 plus 1 plus, I need a little bit more space for 2 plus 3, like this one. And then, because I started to express the decimal number in terms of the binary digit. So yeah, we can also consider that this is actually a 0, 0, and this is 0, 1 in binary digit, a binary number, and then this is 2, and this is 1, 0, and then this is 1, 1. And if you note that, then there is even further concept that this value of 2, and then this value of 2 is expressed in terms of, when it is expressed in terms of 1, 0, what this really means is that it is actually the first qubit is 1, and it is tensor product with another qubit in 0. And similarly, for all the others, yeah, for example, 0, 0 means actually the it is a 0 tensor product 0, and then the 0, 1 or 1, 1, each of them simply means that it is a 0 tensor product 1, and then the 1 tensor product 1, something like this one. Yeah, so this is the implication. And then when you see this, this format, then there is something you might also want to do further. What I mean is that, yeah, if you have a summation of these 4 terms, what do you want to do? Maybe some of you think that, well, maybe this can be factorized. So yeah, let's factorize this expression. Then this one can be expressed as the summation of 0, summation of 0 and 1 tensor product with another 0 plus 1, right? Yeah, if you expand this this tensor product, you will actually obtain this value. So yeah, this is interesting, but this was only, but you might think that this kind of factorization works only when j equals 0. Then what happens if we have j equals 1, not 0? Then if we apply this case, then it is e to the 2 pi I, and it is 0 over 4 times 1, and the second term has the factor of 2 pi I, 1 over 4 times 1, and the third term has e to the 2 pi I times 2 over 4 times 1, and finally the last term has the 2 pi I 3 over 4 times 1. And all these 1 came from j because it was the expression. And then all this value came from this value, which I expressed as a k. And then now now because we started to consider k in terms of the binary digit, so why not we also consider the meaning of these 2? Yeah, so the meaning of these 2 is actually, as all of you are familiar with, it is simply 1 times 2 to the first plus 0 times 2 to the 0. And then now, yeah, what this means is that the exponent part can be also represented as the summation of 2 value. And then we know that e to the a plus b can be simply expressed as e to the a times e to the b. So if we use this concept, then this one is e to the 2 pi I and 1 times 2 to the first, and then 0 times 2 to the zeros, and then it was multiplied by 1, which came from j. And then this one can be also expressed as 2 pi I 1 times 2 to the first over 4 times 1 multiplied by exponential 2 to the I and 0 times 2 to the zeros, and then 4 times like this one. So why did I do that? Yeah, the reason is if you know that the, oops, this one value is actually matched with this one because the value appearing here came from K, and then the value here also came from K. So if this first term is the first qubit is 1, then we will have 1 value here. And then if I have 0 value here, then the second term will be 0, yeah, which is obvious. But the point is, what happens if I split this multiplication and then distribute each of the factor to each of the term, each of the component here? Then what I will have is that I will have e to the I 1 times 2 to the first over 4 multiplied by 1. And then now it is multiplied to the first qubit. And now I can also think that this is the second term has e to the 2 pi I, and it is multiplied 0 times 2 to the zeros, and 4 multiply 1, and then it is 1. So yeah, the second term, second factor came from the combination of these two factors, and then the first factor came from these two. And here I also pointed out that these factor will always match, and these factor will always match. So if you consider the case when, if you compare with the j equals 0 case, now we would have all of these terms. Yeah, so this kind of split is not only limited to the this term, but it is generally applied for all the other terms, because all the other terms can be also expressed in terms of the binary digit, and then all these factors can be also represented in the binary digit, like this case. So eventually, all of these term or all of these factor will have this kind of factor phase factor in front of each of the part. So what happens is that eventually we will have when you factorize this one like before, then it is obvious that each of the term here will have, for example, for this one, it corresponds to this way here. So it would have e to the 2 pi I coming from 1 to the first. Yeah, this looks a little bit unclear. So it is 1 times 2 to the first over 4 times 1. And then, for example, for this factor will appear here as 2 pi I, and it is 0 because this is 0, and this is 2 to the 0th order, and then over 4 multiplied by 1. Then what about this factor? Yeah, it will be similar to this one, except that it will have e to the I, and then instead of 0, it will be 1 times 2 to the zeros over 4 times 1. And finally, this factor will have e to the 2 pi I, and then here it is instead of 1, it will have 0. So 0 times 2 to the first over 4 times 1. And then again, this one case when one actually came from J, and then if we generalize as a J, then what we have to change is that instead of having one here, 1 here, 1 here. They will be just replaced by J, 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 J. And similarly, because that J also appears here and here. So, and then that one eventually appears as here, J, 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 J. So, and then this one, and another thing you have to consider is that for the factor in front of 0 qubit, that means that the exponent part will be always 0. So we don't act, so the entire exponential value will be 1. So we don't really have to keep this factor. So generalization, the result of generalization will look more likely this way. So in front of 0, there is no component, but in front of 1, we will have always this factor. And then another thing you have to note is that the exponent of this power of the, or the power of the two. Yeah, so for the lowest, so in computer science, we call the lowest digit as the least significant, least least significant bit, or LSB, and then this is the second LSB, and so forth. So as we move from the LSB to the most significant bit, then we would have this 2 to the zeros, and 2 to the first, and 2 to the second, and so forth. And then so this expression now is a little bit similar to the target result we were looking for, but still there is some difference. So let me also explain how this factor can be turned into this kind of expression. So this is the summary of what I just showed you. And then the reason I don't have the one time in front of it is because whenever it is one, then it is meaningless. So I just simplify the overall expression in this way. Now, what we are going to do is further consider more general situation. So in the previous page, we only consider n equals 2, which means capital N is 4. And then let's also consider for the case of n equals 3. And then, let me just use the other one. So this is what we had before. And now, we want to consider when n equals 3 or capital N equals 8. So then what is changed is if I have J, then it will be, instead of having 1 over square root of 4, we will have 1 over square root of 8, which comes from the this n equals 8. And then we will have three terms, tensor product, instead of 2, because now we have 3. And then the first term will have, well, let me start with the last term first. Then this will have a similar, it will be thus exactly the same as 2 pi I. And as I said, I won't keep this one anymore, because we always know that it will be 1, and then the multiplication of 1 doesn't do anything. So it is 2 to the zeros, but it should be divided by, not by 4, but it should be 8, because now we are considering n equals 8. So that's one difference. And then it will be multiplied by j, and this should be 1. And for the second term, it will be similar. So it is 2 pi I multiplied by 2 to the first over 8 times j, and it will be 1. And finally, the first term will appear like 2 pi I, and then it is 2 to the second over 8. And then it should be multiplied by j, and then it is 1. And the reason I'm considering here is that, let me give you some more concrete example for the case when j equals 7. then yeah, as we discussed before, this value can be this decimal number 7 can be also turned into the binary number 111, and then we will call the first digit as j sub 1, another one as j sub 2, and another one as j sub 3, and so forth. And then the now, yeah, what I'm going to consider is the exponent part appearing here. Yeah, so yeah, let's think about what happens when we consider this part. So this one is actually 2 to the second multiplied by j, and in this case, even though I just gave you an example of 7, but if we generalize as j sub 1, j sub 2, j sub 3, then it can be generalized as j sub 1 times 2 to the second plus j sub 2 times 2 to the first, and j sub 3 times 2 to the zeros. And then it will be divided by 8, or we can also re-express that as 2 to the third. And then now what I'm going to claim is that these two numbers doesn't matter. And then why is that the case? Because we know that this entire, this part will be eventually multiplied by 2 pi I, and then it appears as the exponent of the exponential value. And then in this case, if we multiply the 2 to the second to the 2 to the second, and then it will be 2 to the fourth. And then also for this this value, it will be still 2 to the third. So they will just cancel with the denominator, and then we for this value, yeah, for this part only, I can say that this is the integer plus only the j sub 3 times 2 to the minus 1, because the multiplication of this is 2 to the second, and then it will be divided by 2 to the third. So this one, and then this value or this value will be eventually multiplied by 2 pi 2 pi I, and then in other words, this integer will just work as the integer multiple of 2 pi, and then in that case, the entire value won't be changed, whatever value each of these. So for this part, we can rewrite in the way that this is actually the equivalent to j sub 3 times 2 to the minus 1. And then in other words, we can also express this one as 0 j sub 3. And what about the second term? For this one, instead of having 2 to the second, we will have only 1. So in this case, not both of these terms will cancel, but only the first term will be canceled, and then the second term and the third term still remains, and then this one, this part appears as j sub 2 times 2 to the minus 1 plus j3 times 2 to the minus second. So overall, this value can be also re-expressed as 0 j2, j3 in binary digit, in a binary number, as a binary number. And that's how we got for this kind of expression. So as we keep go along, and then this will be appears as 0 j sub 1, j sub 2, and j sub 3. So that's exactly what we obtained in this expression. So I hope that by now you are comfortable with this kind of expression. And the next, and yes, so I can summarize that what we just showed, what I just showed you, it can be summarized in this way. And then if we keep, if we have more than small n equals 3, then we would keep having more terms tensor productive with these terms. So the next question is, how can we implement this kind of function in terms of the circuit? So yeah, let's also use a previous example. So according to this expression, what we want for the case of the 3 is the following. Yeah, so if we consider this situation, then let's assume that we have j sub 1 and j sub 2 and j sub 3 input, and then they are all tensor productive. And then for the and let's say that we want to obtain this final result in the last digit. Then if we look at the expression, then what we have to obtain is the following. So it is 2 pi I times 0.j3, and then it should be something like 1. And then how can we from j3 j sub 3, how can we obtain this value? Well, yeah, let's see what this implies. When the j3 is 0, then this state corresponds to 0 plus, and then because it is 0, so this is just a 1, so it is simply 1. And then for the j3 equals 1, then this means that this 0.1 is 1 over 2, and then that 1 over 2 will be cancelled with 2. And so yeah, eventually the value is 0 plus e to the pi I 1, or pi e to the pi I is simply minus 1. So yeah, we will have this this state. And what is the yeah, and then yeah, again, what we need is we need some kind of circuit or some gate which will transform depending on the value of j sub 3. Either it will turn into this one or this one. And then, do you remember? Yeah, and then yeah, if we here I intentionally omitted the normalization factor for simple discussion, but yeah, this is exact. This is correct expression. And then, do you remember what kind of transform? Yeah, this kind of what is this transform was called? It was called as Hadamard gate. So all we have to do is just add the Hadamard gate in front of the J3. So that's how we can obtain. And then what about the second term here? Yeah, so second term might look a little bit more complicated. So compared to the last term, we require 0 plus e to the 2 pi I and j sub 2 and j sub 3 and so forth. And then for this case, again, to implement point j sub 2, all we need is just to add the Hadamard gate. Then depending on the value of the j sub, let me draw closer. So all it does is yes. So if we just add this Hadamard gate, then it will implement yeah. Then the 0 value won't get any phase component, and then the 1 value will get the phase component depending on whether the value of depending on the value of j sub 2. Yeah, this might get some proper component, but we still need to implement this part, and then this part can be actually yeah. And then if you consider what kind of phase we need to implement, then depending on the value of the j sub 3, we need some kind of gate. And then if you consider the action of the action of this gate or this gate, then what it should do is for the zero, and then if I represent the function of the gate in terms of the matrix representation, then for the zero basis, we should not have any change. But for the for the one basis vector, then we need to have some additional phase factor. So what we need to do is we need to add something like 2 pi I, and then this one this digit corresponds to 1/4, or we can say that it is 1/2 to the second. So by having this kind of circuit, we can actually implement this kind of result. And then what about the third one? Well, that is also similar. So it is 2 pi I, and it is 0.j sub 1, j sub 2, and j sub 3. And it is like this one. And then in this case, for the first j sub 1, it is equivalent to having just a Hadamard gate. But for the contribution of this j sub 2, it is the same as the contribution of this guy. So what we can do is we can represent the action of the gate in terms of the matrix, and then it will be exactly the same like before. So 2 pi I, and it is 1/2 to the second. So we need this kind of gate controlled by j sub 2. And then what about the j sub 3? From the j sub 3, what we need is some additional gate. And then for this one, we don't want to do anything for the 0 state, but for the 1 state, we need to add the phase, which is 2 pi I, and 1/2 to the third, something like this one. So the phase, this phase factor will be added only when j sub 3 is 1. So this is the general. So this is a circuit to implement this kind of three qubit situation. So So if I just generalize what I showed you, then that kind of circuit can be generalized into this form. And then I hope that by now, this circuit makes more sense before compared to when you saw this circuit for the first time. And then as you remember, each of these gate has different phase components. So we would just have this kind of vector for each of the different gate. So so what we have been working on is basically we want to implement this kind of transformation. So if we express the input state J in terms of the binary notation, then these are the binary digit. And then for each of the and then depending on whether each of the value is 0 or 1. So whenever you have one value for this, then you want to have this kind of output state. And then for different bases, then you want to have different result like this one. So that's how we can obtain all of this like this. Then if I summarize what we did so far in the insurance algorithm, what we do is we first create the superposition of all possible value of A, and then we apply this A value to the calculation of the power of some random number r mode mode n, and then the result of this process is we will be left with this kind of superposition of terms. And then yeah, here I just collected all the terms with the same remainder, like this one. And then here we can find out some kind of pattern, like a 0, 4, 8 something, and then or 1, 5, 9. And then if we can describe this situation as it is x0, 0 plus x1, 1, and x2, 2, and so forth. And then we want to convert this one through the QFT that such that the result will be y sub 0 with the 0 and y sub 1 with 1 and so forth. And then each of these y sub k is actually the corresponds to the discrete Fourier transform. Discrete Fourier transform corresponding to this given sequence of x0, x1, x2, and so forth. So this sequence can be considered as this one because of this one has 1 as the coefficient of 0, and then coefficient of 1 vector is 0, and then coefficient of the 2 vector is 0. So the sequence corresponding to this superposition is 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, and so forth. And for the second case, it is 0, 1, 0, 0, 0, and 1, 0, 0, 0, and 1, 0, 0, 0, and so forth. And then for both of the case, the frequency component or the period is actually the same. So yeah, whichever state you try to transform using the QFT, the surviving term will be the same, and then the only difference is the phase vector multiplied in front of here. And if we just assume that we measure some value like k equals 120, 192, yeah, for example. And then what that means is that that k corresponds to one of these vector. And then in the last lecture we also learned that k vector, yes, single k vector can be single k vector means that it is a square root 1 over square root of n, and then each of the term will appear like a minus 2 pi I, and then k times 0 over n, and the next term is 2 pi I and k over n times 1, and and e to the minus 2 pi I, k over n times 2, and so forth. So we will have this kind of sequence. And then in this case, for this problem, capital N is 256. So what that means is that, and then we know that this is kind of sampled sinusoidal function. So we can roughly think what will be the period appearing showing appearing from this sequence. But we should be careful because the period is not 256, but if we consider that the ratio of k over n can be reduced, so that 192 over 256 can be reduced to 3 over 4, which means that this part can be reduced down to 3 over 4. And then that means that 2 pi I times 3 over 4 times some j. And then when do you think this will repeat? Whenever j increases by factor, j is increased by 4, then because that 4 number will cancel with each other. So for example, when the j is 0, then this factor is 0. But after j becomes 4, then it will become a minus 2 pi I times 3, which means that this is the integer multiple of 2 pi. So yeah, the same value will repeat. So in this case, the period is 4, not inverse of this value. So yeah, if you just think that this is the frequency, then typically with the continuous function, you think that the inverse of the frequency corresponds to period. But for the discrete sequence, the period does not necessarily directly related to the it's not just the inverse of the frequency component, but you should actually find out what is the proper denominator after you take the after you reduce the fraction. So and then the more systematic way, here I just gave showed this example to give you an intuition. But if you want a more systematic way, then there is some method called as continuous fraction, which is described in the textbook. So I recommend that you read that part and then understand how we can find out the period based on the measurement result of the QFT. So this is the end of the explanation about the Shor's algorithm. And then more property can be found by working out some of the homeworks. Another important class of the algorithm is called as a Grove algorithm. And the main purpose of the Grove algorithm is search some kind of big space of data. And then, for example, if you think about some database, then there will be a lot of data. But in a modern database, to improve the searching efficiency, they generally sort the data so that the search can be speed up by using the binary search or other types of search or tree search. However, in this case, we simply assume that the data is unorganized. So there is no underlying structure the way the data is stored. And then the only option we can search the data is that assume that we assign each of the data with some kind of index. So 0, 1, 2, and then there will be a lot of index. And then the total number of the index is, let's say, we will assume that it is n. And for the simplicity of the discussion, we are also assuming that it is capital N is 2 to the power of the number 2. So in this case, the question is, let's say that there are a lot of possible input, and then among these, maybe this value might be the solution, but sometimes, depending on what you are searching for, sometimes there might be more than one solution. So there might be another solution and also another solution. So I will write that the number of the potential solution as m. And so this is the definition of the problem. And then I will further assume that there is some kind of function. And then if you supply this index value like from 0 to n-1, and then I will call this value as index value as x. And then if I provide one of this value to here, and then let's say that if the index 2 where index 2 is the solution, then if I provide number 2 as an input for this function, then this function will return the value of 1. However, if we provide some value which is not the solution, then the return value will be 0. So that is just the definition of the problem. And the question is how quickly we can find out at least one solution. So that's the growth search problem for the growth search algorithm. And then let's also develop a little bit more details. So here the x might be multiple bits. So we are assuming that the x is n bits, and then we provide n bits. And then there is some black box, and then, well, not necessarily black box, but some box. And then the assumption is that when this box receives the input value of x, then internally it will calculate the f of x, which is described, which has this kind of property, and then the output value will be still the same value like x, but there is additional auxiliary qubit, and then if you provide the value of q, then the output of this one will be q XOR f of x. Like this. Yeah, so this is our assumption. And then we want to implement this kind of box using the quantum process. So what we have to do, and then if we can implement such kind of box, then the description for the, and then this will appear as a unitary operator, and the description of the unitary operator is the following. If we provide some vector as an input to this unitary operator, and then this vector can be represented as the tensor product of the input value and some auxiliary qubit. Then the output of this unitary operator is that tensor product between the x vector and then the this kind of vector. So that's the output state of this unitary operator. And the next thing we want to, you might actually wonder whether we can always find out this kind of unitary operator. And then that the answer to that one is still true, because we know that any arbitrary calculation function in classical computer can be represented by the digital logic. And then we also know that any arbitrary digital logic can be implemented by quantum gate, because there are universal gate in the there are Toffoli gate, or the other types of gate which is reversible gate, and all those reversible gate can also implement the digital logic. So in principle, we can implement any kind of digital logic using the quantum process or unitary gate. So that is guaranteed. And then once we have this kind of unitary operator, the next thing we will consider is we will provide this kind as an input for the Q. We will provide the superposition state. And then if we provide this kind of superposition state, and then the output has this kind of relation, then we in the discussion of the Deutsch's algorithm, we learned that if we have this kind of thing with this input, and then if the with this kind of function, and then if this function can have only 0 or 1, then the final state of this state will become like this one. So if you can remember, go back to the discussion of the Deutsch's algorithm, and then we already derived this one. But we also note that if the input is like this one, then this phase is also affecting the overall quantum state. So the you can also think that this phase is applied to the entire state, entire input state. So that's the definition of our problem. And then now what we are going to do is we will, so this is what I just described. So the box here is called as O, and then we will have the action of this box O is like can be described in this way, and then the final result of this one is like this. And the final result of that function is can be expressed in this way. But now we will we will simplify the situation a little bit further. Here, what we can say is that all this this additional qubit input and then the output of this qubit part can be considered as the internal part. So the output, the external interface is determined or defined in this way. And then you can think that the entire box has the input qubit of n, and then the output qubit will be still n. But if we provide this x, then we can build some box, or we can build some unitary operator, which will add additional phase factor, which can be described as a 1 to the minus 1, minus 1 to the f of x. So that's because we somehow, I think, consider that this this qubit is some internal part. So even though the at the end of the process, it will still appear as this one, and then we don't measure it. And then in that case, we can consider that the phase factor of this vector is only changed by this amount. So from now on, whenever I'm talking about something called as oracle or quantum oracle, then I'm basically talking about this kind of box. And then this one only accepts the n qubit as an input, and then the output will be still n qubit. And then the quantum state, I cannot say the quantum state is not completely changed, is not constant, because we will have some factor, and then if the this vector is in a proportion, then depending on the value of x, sometimes the sign will be changed, and some other component won't, the sign of other components won't be changed. So that's what we are interested. But now what we are going to do is compare the performance between the quantum algorithm and the classical algorithm. And then for the classical case, let's say that if I have the sample of 100. Oops. Yeah, so let's say that n is 100. So there might be some 100 indexes, and then among those, if there is only 2 solutions, so in that case, if m is 2, then on average, how many times do you have to search, or do you have to repeat before you can actually find the solution? And in that case, we don't know which one will be the solution. So on average, we have to repeat about 50 times, because we know that every within the 50 samples or 50 input, there might be one solution. So on average, you might have to repeat 50 times. And then if I just calculate a big O notation with the big O notation, then 50 can be obtained by n divided by m. So this is the order of the complexity for the classical computer. And then if you follow what I'm going to explain about the Grover search algorithm, then we will obtain the conclusion that the search can be reduced down to square root of that n over n, n over m. So depending, for example, if the m was 4, here, and then that means that for the classical case, we need, on average, we need to repeat the query maybe about 25 times. However, for the quantum case, the number of query we should do is only 5 times. So that will be a lot of speed up. So that's why we are interested in the growth search. And then before we go to the detail of the growth search, let me give you some overview of the growth search. In the previous discussion, I mentioned that typical quantum algorithm generally has 3 steps. And then the first step is generally creating the superposition state. And then the growth search also does the similar thing by creating some superposition of all possible input. And then it does some internal process. And then we repeat that internal process several times and measure it. And then compared to other process, other algorithm, you might think that there is no interference stage. However, for the growth search, generally each of this box is composed of processing and some interference, and processing and interference, and so forth. So that's a little bit different pattern, but except that this one still has the overall structure of superposition generation, and then process and the interference, and process and interference, and finally we will measure. So overall this one has a similar structure. So what we are going to do is investigate what does this box look like. Now, what we want to do is the following. So we will start with the definition of 3 different vectors, and then in this case, let me use some. Let me give you some concrete example. So let's assume that I want to. Our problem has 4 different input, and then let's say those inputs are 0, 1, 2, 3, and assume that only 2 is the solution. In this case, the alpha vector is the sum of all x which are not the solution. So meaning that alpha is basically the summation of 0 state and 1 state and 3 state. And then, of course, this cannot be a good vector because it is not normalized. So we have to do the normalization over square root of 3. And beta is composed of only the solution. So in this case, specifically, it is there is only one solution. So in this case, the normalization factor is 1. But if there are more than one solution, then we know that the number of the solution is m. So the solution will appear here. And then psi is the summation of all the possibilities. So in other words, psi is 0, 1, 2, and 3, and it is normalized over 4. And then and now what we are going to do is assume that first you should note that these 2 vectors, alpha and beta, are orthogonal to each other or orthonormal to each other. And then the way you can prove that they are orthogonal is if you just take the inner product between these 2 vectors, they are all orthogonal to each other. So there is no way why the inner product of these 2 vectors will vanish. So they are orthogonal, and then I normalized, so they are normal. So I can say that they are good orthonormal vectors. So I can draw that they might appear like alpha and beta. Oops. Like this. And then we can also think that the psi is the summation of this component and one vector. So in other words, this can be considered as square root of 4, and summation of 0 to 3 is this part, meaning that it is square root of 3 alpha, and then the vector 2. Oh, sorry, I drew the I grouped incorrectly. Yeah, so it is 0, 1, and 3. So these summation of these three components corresponds to square root of 3 times alpha. And for this this solution part, it will maybe you can say that it is square root of 1 beta. So in general, we can say that the psi can be expressed in terms of can be expressed as a linear combination of alpha and beta, and then the denominator of the coefficient is the square root of total number of n, which is square root of 4 in this example, and then this value came from m, the number of the solution. So yeah, the numerator in front of the beta is square root of m, and then the other part is a difference between the n and m. Yeah, so yeah, that's how we can obtain here. And then this kind of decomposition also implies that the psi vector can be always represented as a vector inside the plane defined by alpha and beta bases, because they are also normal to each other. I can say that they are the basis of the new plane, and then the psi appears like here. And then we can also think about the angle between these two vectors, and yeah, we can do a lot of things. But before we continue, let me also introduce the concept of the reflection about some vector. So yeah, here the important point is that if let's say that we are given some so not only it is alpha and beta and gamma, but in general, let's say that I am given some arbitrary vector gamma here, and then some arbitrary vector phi here. And what I want to do is change this vector with respect, or reflect this vector with respect to this vector, meaning that if I have some angle here, then I want to reflect with the the same vector, same angle, and then the new vector will appear like this one, gamma prime appears like this one. So how can we do this? Well, if you remember how we did the how we proved the Gram-Schmidt theorem, then what we did is we made a projection of this vector on the this another basis vector. So if I just assume that this is some kind of basis vector, then what I want to do is find out this first this component, and then I also want to find out some additional another component which is orthogonal to this phi. So if I decompose gamma in terms of the parallel component and then orthogonal component, then gamma can be the summation of these two. So gamma, yeah, and then if I call this parallel component, I will just use the parallel, and then this orthogonal component as orthogonal, then the gamma can be represented as orthogonal parallel plus orthogonal component. Then how can I express this reflected vector in terms of this parallel and then this orthogonal component? Well, yeah, if you look at this geometry, then it is obvious that the reflective part should be expressed as parallel minus orthogonal component. So that's what we have to do. So yeah, geometrically it is obvious. So how can we implement mathematically? Well, the first thing is we have to find out the parallel component. And how can we find out the parallel component? By using the projection operator. And then yeah, here I assume that the phi is already normalized vector. So what I have to do is apply the um, projection operator on the gamma vector. Then it will be it will only select or filter out this parallel component like this. Then how can I find out this normal this vertical the normal component? Well, yeah, we know that gamma is the summation of these two. So if I subtract this component from gamma, then this we can obtain this one. So this is yeah. So yeah, here I just summarize that the parallel component can be obtained by this projection operator, and then this normal vector normal component can be obtained by subtracting this parallel component from the gamma, and then I can express this way. And what we are looking for is this gamma prime. So now what I have to calculate is the subtraction of this normal component from this parallel component. And parallel component minus normal component, and then parallel component is this one, and then normal component is this one. So if I just plug these things together, then it should be 2 times phi, or 2 times the projection operator minus identity operator, and the entire part is multiplied on the this gamma vector. So here I just generalize the idea. So whenever we are given some phi and gamma, then we should be always we should be able to find out the reflected reflection always. So what we want to do in the growth search is to use this idea. Yeah. So again, remember that alpha is the vector composed of all the non-solution, and then beta is composed of only the solutions. And the situation is that, let's say that we somehow our initial vector is started with the summation of all the indexes. Like here before, I had the psi, which is the summation of all the possible indices. And then our goal is to make this vector as close as possible to the beta vector, which is composed of only the solutions. And then we know that this beta vector is orthogonal to the alpha vector. So our goal is, whatever we do, we want to eventually move by going through some of the unitary operation. This vector might be changed to somewhere else, and somewhere else, and then somewhere else, and it might move around. But eventually, we want to move the final vector as close as possible to the beta vector, like here. Yeah. So this is our goal. Yeah. So the final state of the quantum state should be parallel or as close as possible to the beta vector. Then how can we do that? Well, yeah, first of all, let's see what we can do. And then as I mentioned before, this psi vector can be always considered as the not only the psi vector, but any vector inside this inside the plane created by alpha and beta basis. Then they will be always have some kind of component alpha plus beta component with b coefficient. Then if I want to perform reflection with respect to alpha, in this case, the problem becomes simpler, because all we have to do is, if we want to reflect this one with respect to alpha, then what I have to do is just to replace this sign to minus sign. So it does not require that a projection operator because it is already kind of decomposed into the parallel component and then normal component, orthogonal components. So yeah, this is all we have to do. And if so the first step generally starts with the psi, and then this will be reflected with respect to the vector alpha. And then finally, what we do is we want to now do the reflection of this vector with respect to the psi. And then in this case, we can use the result we had before, meaning that the reflection with respect to some vector is that so if I say that the first operation from here to here is expressed in this way, then what I have to do is I have to apply the operation to psi minus I and this minus I. And then if I apply this operator on top of this one, then I can be, I should be able to reflect this one all the way to up to here. And then what is the result of this operation? Well, we started with our starting point was this vector. And then if we assume that we had angle between this psi and alpha, and then the angle was theta over 2, then the first reflection with respect to alpha will move to here. So we will have the total angle of theta between psi and this reflected vector. And finally, if I do the reflection of this vector with respect to psi, then this will go up to go by another theta. So overall, the angle from the initial vector to the new vector is that this amount of angle is changed by theta. And then what happens if I just repeat this process? Well, then the next in the next stage, the starting point will be here. So, and then this vector will be reflected with respect to the alpha again. So if I do the reflection with respect to alpha, then I will have the new vector, which will have the theta 3 times theta over 2. And then, yes, and then the total, and now, and after this reflection with respect to alpha, then I also want to do additional reflection with respect to this psi. So the total angle between the psi and then the current vector is actually the summation of 3 times theta over 2 and theta over plus theta over 2. So it is the new vector will be moved to another 2 theta. So what happens is if I just repeat this process, then the new vector will be rotated by theta, because the first procedure of reflection to here and then go back here, you're moved by theta, and then additional reflection with respect to alpha, and then the additional reflection with respect to psi moved additional to theta. So the next step was additional theta here. And if you just keep doing it, then it will move by theta and theta. And then the question is, if we can find out the amount of size of this one initially, then we know that the total angle between here and between these two should be 90 degrees. So if we divide 90 degrees by this amount, then we should be able to tell how many how many procedures we have to apply until we can arrive around this vector. So that's the idea about the Grover search. And then such kind of procedure can be expressed mathematically. In the previous picture, what we wanted to do first is the reflection with respect to alpha vector. So what we should do is if our current vector can be expanded in this form, then all we have to do is change the sign of this one. And how can we only select the vector v and then apply the minus sign here? Well, the solution is already embedded in the oracle operator. If you remember our discussion in the first page, then we wanted to somehow we wanted to build a quantum oracle O operator, which and then this the function of this one is that it will change the sign of the coefficient or the probability amplitude only for the solutions. So if x is the solution, then this component will become -1. But if x is not a solution, then the f of x is 0. So it doesn't do anything. So just by applying the oracle operator on some vector, then it will only flip the sign of the component with sign of the beta vector component, and then we know that a vector component, beta component is only composed of all the solutions. So yeah, the f of x will be always 1. So yeah, it is guaranteed that the sign of all those vectors will get additional minus sign. So that is how we can implement this first reflection with respect to alpha. Then how can we implement this additional rotation with respect to psi? Well, that's also, if we possible, if you look at the shape of the reflection operator necessary, if we want to do the reflection with respect to psi, then this should be the shape of the operation. And then we know that psi is a summation of all the possible values, and then it is the equal amount of superposition, meaning that there is no additional weight on some other different state, but it is equal probability for all the values. And such kind of superposition of all the possible value can be generated by applying the Hadamard gate on the 0 state. So what we can do is that psi can be expressed in this way. And then what about the entire projection operator? Not projection, but the reflection operator. Well, then we have to plug in this relation. Then this will be Hadamard to the n, and then 0 to the n, and then the other part will be also expressed in this way. And then we will have this identity operator. And then we know that square of the Hadamard gate, meaning that if we have h, then, or yeah, I should say h squared, then it is actually the same as the identity. So identity operator can be also decomposed into the Hadamard gate n, and then another Hadamard gate n. So yeah, if I just replace this one with this, then I can actually rewrite the entire expression in this way, because both of them has Hadamard, two of the Hadamard on the left and on the right. And then for this one, yeah, it also has Hadamard on the left and the Hadamard on the right. So if I just collect all the common factors, then they can be expressed in this way. So the overall reflection, or the two-step reflection, can be represented in terms of the gate like this way. So the first reflection about alpha can be just is just the oracle operator, and then the second step of the reflection with respect to psi can be decomposed into these three steps. So the first step is appearing here, and then second step or second gate appears here, and then the last Hadamard gate appears here. So and then if you look at what's the meaning of this one, then the we generally have well, yeah. So let me rewrite this one. If we continue to consider the example of n equals 4, then the this part means that it is 2 times 0, 0, and 0, 0. And what about the minus? What about the minus identity? Where identity is 0, 0, and 0, 0 plus 0, 1, 1, 0, 1 plus 1, 0, and 1, 0. And finally, it will be 1, 1, and it is 1, 1. And like this one. So if I just add, subtract the entire thing from this one, then we know that this is because this one has a 2, and then 2 minus 1 is just 1. So the sign in front of 0, 0 will be plus, but the rest of the other options will all get the minus sign in front of it. So that is actually correspond to changing the sign for all other possibility except the zero values. So this 0 does not mean that only one qubit, but this 0 is the expression of the entire value in terms of the in the decimal number. And then if the decimal number is not 0, then all the other sign will be flipped. So you might feel like this is a little bit a strange gate, but we actually had a very similar gate before. Yeah, so if you remember Z gate, the function, the notation of the Z gate is that for the 0 value, there is no sign change, but for the 1 value, there will be a sign change. And then if we extend this concept, then the if we are considering the considering 4-dimensional space, then it will have four dimensions, and then all the other value will be still minus 1. So yeah, this is kind of extension of the Z gate, and then we call this kind of gate as a phase gate. So now let's combine what we just covered up to now. Yeah, so in the previous page, I mentioned that this kind of combination of oracle box and then this kind of operation corresponds to the so the first oracle box corresponds to the reflection with reflection of any vector inside this inside the plane created by alpha and beta basis, and then the oracle the action of the oracle operation is that it is the reflection of any arbitrary vector with respect to alpha. So it will first go to here, and then the combination of these operator corresponds to the reflection of the next vector with respect to psi. So yeah, it goes like this one, and then we call this combination as combination of these gates as the Grover operator. And then we know that single Grover operator will move if the angle between psi and alpha is theta over 2, then we know that single Grover operation will rotate this vector by theta. And what happens if I apply this Grove operation one more time? Then, as I mentioned, it will go down to here, and then it will be reflected again, and then it corresponds to additional rotation by theta. And then if I apply another Grove operation, then it will also rotate by theta again. And then the question was, what is the optimal number of Grove operation? And then to find out this total number, yeah, so here I just say some number, and then this number can be estimated by considering the fact that the angle between alpha and beta is 90 degrees. And then if we know this value, then by dividing pi over 2 by theta over 2 or pi over theta, then we should be able to tell how many. And then yeah, in this case, we know that if we apply the Grover operation for m times, then that means that the final angle will be theta over 2 plus m times theta, or m plus 2 1 over 2 theta. And then what we are looking for is when does this value get closest to the pi over 2. And then to figure out this m, we should be able to tell what is the theta over 2. And then theta over 2 is the angle between these two vectors. So how can we find out this theta over 2? Well, if we use the inner product, then we know that cosine theta over 2 is the inner product between psi and alpha. And then both of the psi and alpha are normalized. So we should be able to just, if we just calculate the inner product between these two vectors, then you might get this value. And then you might also say that, well, yeah, that's a good idea, but how can we know the alpha vector? Because at this point, we don't know about the solution. So how can we construct this vector? Well, yeah, that's actually quite straightforward, because yeah, when I define the alpha vector, I know that this vector will have the component like in the previous example. Yeah, I simply assume that this one has these three components over 3, and then we know that psi is the summation of all those 4 vectors, 0, 1, 2, 3. And then if I take the inner product between alpha and psi, then we know that the denominator will be 3 times square root of 4. And then what about the numerator? We know that there will be only 3 components which will not vanish, and then all the other multiplication will just vanish because they are also normal to each other. So can you tell what value will appear in the numerator? It should be 3. And is this information require the knowledge about the solution or exact solution? Actually not, because yeah, here, yeah, even though you might say that we intentionally didn't include the 2 vector because it is solution, but actually to obtain this value, all you need to know is the number of the solution, but not exactly which one. And then even if you didn't know which one is the solution and which one is not, but we know that psi will have all those vectors, and then alpha will have only n minus, yeah, alpha vector will have only n minus m components. So this is the value of 3 is simply the n minus 3 and is n minus m. And what about this value? This value is simply 4. 4 is actually the special case of n. And then what about the 3? It is again n minus 3, n minus m. So the overall value should be n minus m. And to obtain this value, we don't need the concrete idea about the solution. All we need is the how many solutions do we have? How many solutions we might have inside there. So yeah, those information will be generally given at the beginning. So just by considering that information, we can immediately find out this theta, and then the rest of the calculation should be straightforward. So and then yeah, once we figure out that, then let's say that we obtain the by applying the necessary amount of Grover operation, we might get very close to beta, but not exactly beta. And then you might be concerned that even if we have this vector, because this vector is still the superposition of beta and alpha. And then if you measure, sometimes you might get the component in alpha rather than in the beta. Well, so that is the problem, but we can immediately check whether our solution, our result is correct or not. And then if not, we repeat this algorithm one more time. And then there is a very high chance that the next time we will obtain one of the vector in beta rather than alpha because it is very close to beta. And then, yeah, of course, in the second trial, we might still get something with from alpha, but we know that only by repeating a few times, we will eventually obtain the value in beta. So that's yeah. You might there might be a little bit of overhead in terms of how many times we might need to repeat this algorithm more than once. But there is very little probability that we actually need. And then even if we got the wrong answer, we should be immediately tell whether it is correct or not. And then, yeah. So the total number of the average number of the um, um, calculation for the oracle is much smaller than compared to the classical counterpart. Okay, so yeah, that's the idea behind the Grover search algorithm. And then I hope that you can work out some of the details. So yeah, this is the yeah. So yeah, I will stop explaining about the Grover search algorithm, and then from next time I will move on to the different topic.